might want to add in.
You have time till
How much time I have?
5:45.
Okay, so it's 4 o'clock now.
4 to 5:45.
No, but when do we start?
4.
4 o'clock? Oh, right now.
That's okay.
Oh, okay, so no time to waste. Windows 7 has issues also. Love it.
Have that?
I gotta wait for the reboot.
Oh.
It got jammed up. I put it in before I logged in. Didn't like it.
State University of New York is Brooklyn Poly, right?
My
You studied
master's.
in
Yeah,
Brooklyn Poly.
yeah. That's what it was called, Brooklyn Poly then.
Yeah, at that time.
Yeah.
And it's not
Then
State
then it
University.
changed to New York Poly, and then it changed to.
State University.
Yeah.
Yeah. Did you hear anything from? Yeah, I think a lot of people.
Copy. And paste. That's big, wow. 94 megabytes.
Oh. Is this height okay? Or you can reduce it if you want.
Okay.
If you go down too much, and then you can't put that.
And red, good. Yeah, wait long enough, students still coming in.
Ah, that's good.
Good afternoon.
pleasure for me to introduce my friend, Mark Adamiak. He's, I'll be doing injustice if I don't read this. So that is why I told him, he said, make it short. No, I won't do that because you need to know how good he is and how much he has contributed to the industry. So Mark is the Director of Advanced Technologies for GE Smart Substations and he's responsible for identifying and developing new technology for GE substations and protect and control. Unlike me, I was teaching you only 1920s and 30s. He is in the 21st and future. So what we have looked so far is only the past, and he will take us to the future, just like Bogdan did on the microprocessor-based relays. He is a graduate of Cornell University. He did his undergrad, and then from Brooklyn Poly, which is State University of New York, he did his master's. And then he worked for AEP R&D, where he was, if you go back and look at the history of Synchrophasors, you can see Mark standing next to a panel there as an engineer, as a student intern, I think, probably.
Right out of college.
Right out of college. And then that is there as there. So he worked under great people, Arun Fatke and Stan Horowitz.
And Jim Thorpe.
And Jim Thorpe, all great people in power systems. And in 1990, I think he joined GE. And then ever since he has been instrumental in developing a lot of standards in the industry. He's a fellow of IEEE. And also, he has contributed a lot for 61850 for interoperability on the relays. And then what else? He is a U.S. regular member for the SIGRE Protection and Control Committee, and he's a registered professional of State of Ohio, and he's a GE Edison Award winner. Please welcome. Please join me in welcoming Mark.
Thank you, Pratap, and good afternoon, everybody. It's good to be back here again. This has become an annual tradition. This is my third or fourth one, Pratap? Third. So I always enjoy coming out here and seeing what it's like after and post-winter up here. So as engineers, we're always looking to how we can do things better. This is best illustrated by, there were 4 people out playing golf. There was a priest, a doctor, a lawyer, and an engineer. And the foursome in front of them was playing very, very slowly. And they're complaining amongst themselves, why can't they play faster? Pretty soon the greenskeeper drove by and they flagged him down. Stop, please go talk to those golfers in front of us. See if they can play faster. The greenskeeper says, alas, they're blind golfers. The manager lets them play 1 day a week for free. Well, the priest right away says, I'll pray for them that they can recover their eyesight. The doctor says, I know some great ophthalmologists I can put them in touch with. The lawyer says, I'll sue the bastards that did this to them. But the engineer says, why can't they play at night? So as engineers, we're always looking to do things in a better way. So what we're going to talk about today is how we can better serve people in the electric utility industry. And we're going to look a little bit at what the future is in power system protection and control. Found a keyboard? Is this a touchscreen by some chance? No. I need...
It is a touch screen, but you have to.
Oh, pen touch.
The pen touch.
Security alert. Enable external content. Okay, so what are the challenges we face in the power system? So the world's population right now estimated at 6.76 billion people, and you can see from the picture to a large extent. I guess I should use this as far as highlighting goes. This is being taped, so it's. Now, question is, where are we going in the future? Speaking of California alone, right now in California, they expect the amount of electricity used will double in the next 20 years. Presents some sizable challenges. How do you get more power lines into Los Angeles? I mean, the freeways alone just run rampant all over the place there. So by 2030, we're looking at doubling the amount of electricity demand in the world, not just the U.S., but in the world. We're a little faster at an increasing power usage here. And this gives you a flavor for where in the world we're going to see power expanding. Clearly, the biggest area right now is in Asia. India alone is looking at putting in two 1,200 kV lines that will be able to bring on the order of 5,000 to 6,000 megawatts of power from the hydro areas near Nepal down into Bangalore and into New Delhi. By 24, 3 times. So even now, as we start planning for the future, plans have to be made for how we're going to meet this growth. And you see some of the major growth areas being South Africa and South America. The Amazon rainforest is still staying pretty open right now, so that's good news there. So what are the challenges we're looking at as we go toward the future of the power system? So 2% per year, but you take that over many, many years and you have significant growth. Environmental, everyone is concerned with climate change. They stopped calling it global warming now because it was actually colder this past year. So now they changed the name to climate change. It's kind of interesting. What is clear, and I can speak that the CEO of General Electric has identified this, is we are migrating toward a gas economy. I live in an area of Pennsylvania, which is on what's called the Marcellus Shale. There are now some 1,700 fracking wells throughout Pennsylvania that's providing an abundance of clean burning gasoline for the power industry. In the area in Pennsylvania where I'm from, there has been about 20 gigawatts of coal-fired power plants that have shut down and been replaced already by natural gas power plants. You may or may not be aware, but natural gas plants are significantly more efficient than coal-burning power plants. A coal plant will achieve about 40% efficiency. Today's what's called combined cycle gas plants can hit efficiencies of 60% plus. In fact, GE right now is in the midst of testing a next generation unit, and the numbers are not quite in yet, but it's expected to be a little bit north of 60% efficiency. Aging infrastructure. The transmission grid in the U.S. went through a major period of stagnation. There were literally 15 to 20 years where there was no incentive to build new transmission. As a result, we've kind of went into a lull, but now we're seeing an increase in transmission, even again, throughout North America, throughout the world. But as a result, 20 years ago, the infrastructure that was in place, most of the grid in the country was really put in place in the 50s and the 60s. In that time frame, the growth of electricity was 7%. If you do the math, that means you're doubling the size of your power system every 10 years. And that's what the growth period was in the 50s and the 60s. It started leveling off in the early 70s, which is when there was the drop-off in the transmission infrastructure build-out. California alone right now, California is delaying building of new transmission. The new transmission would cost $2 billion to to build what literally has to be built in California, if it finds place to build what has to be built. What they're doing instead, they're putting in what are known as remedial action schemes. You'll also RAS. The acronym is RAS, Remedial Action Schemes. A remedial action scheme says if power line number 1 is overloaded, and power line number 2 is overloaded, and power line 3 just trips out, what do I do? Think of riding a bicycle up a hill, and you're carrying a heavy load, and all of a sudden the hill gets a little steeper. What do you got to do to make it up the hill? You throw stuff off your back, off the backpack. This is exactly what remedial action is. When the generation can't keep up with the amount of load necessary in a given region, it will automatically shed load. You may remember, most of you are old enough here, 2003, we had the major blackout in the East Coast of the United States. Post-mortem analysis pointed out that if as little as 500 megawatts of load had been shed in the Cleveland, Ohio area, the blackout would not have occurred. In fact, as we look forward to the future, this is one of the key enabling technologies for the future. It is going to be automatic remedial action. Well, I think I'll talk about that later on as we go through the presentation. 60 to 70% of the transformers in this country are old. Transformers fail because of age. There's just simple deterioration of insulation. All of the transformers built 30, 40 years ago are paper wound. Paper is cellulose-based. Cellulose decays over time. So they're all ticking time bombs, just waiting to explode. And unfortunately, a lot of them do. Although a lot of that sometimes happens for poor engineering design. I used to work in the utility field, and I used to work for a company called American Electric Power. And at one point in time, they lowered what's called the insulation level for the transformers from 2,000 kV to 1,500 kV. Lo and behold, the number of exploding transformers doubled in direct correlation with the BIL level. So they changed it back to the original BIL level, and the explosion stopped. The fire safety concerns. Arc flash. Anybody ever hear of arc flash? If you've ever seen like a short circuit, this is becoming more and more of a concern in our industry. It's always been around, but it seems to be becoming more prevalent and definitely a higher visibility. There are new technologies coming out now that can actually detect an arc flash. In fact, if you think of an arc, what are the characteristics of an arc? Number one, it has bright light. So light becomes one of the primary detectors of an arc flash. This is like when a circuit breaker is told to open and it doesn't quite get there and kind of blows out the front door. So detecting light is very, very fast, but you turn on the light in the room, that also is light. So how do you differentiate between that of a flash and a light turning on? Well, an arc has sound. So by correlating sound and light, it's another mechanism for detecting the arc flash in a piece of electrical switchgear. What does it cost for a power outage? Estimates are right now that it's $150 billion per year as a result of power outages. The 2003 blackout alone, that one blackout, was estimated at $10 billion in lost revenue because of businesses shut down, people sent home, and things like that. This kind of gives you a flavor. Notice what the orange is, California. That's where the biggest number of outages and costs are. Like, it just costs a lot when you do anything in California. And I don't know if even staying there. In fact, I don't know if you've heard recently, another challenge that we have now in the utility industry is terrorism. Just recently in California, a terrorist went in, or a group of terrorists went in, and they shot up 11 power transformers in a 500 kV switchyard. They took out the entire switchyard. In fact, if it had been in the summertime, there would have been rolling blackouts throughout all of California. So this has now become the new threat. The power grid is wide open. You drive across Ohio, you drive across Minnesota, just thousands and thousands of miles of open power line. Anybody with a little knowledge, could wreak havoc with the power system. The most vulnerable, obviously, are the transformers, because you take out a transformer and you're looking at 18 months to 24 months to get a replacement. We do have, coming up in the rear, the renewable and distributed energy. These are great sources, but unfortunately, at this point in time, they only account for a small fraction of the total power generation in the world. In the U.S. right now, I think the number I last saw was that at least 60% of the electrical generation in the U.S. is still from coal-fired power plants. Gas is picking up dramatically with the fracking revolution. Nuclear has flattened, or as a percentage, has actually gone downhill. I'm hoping that in your generation, you're going to be seeing the results from fusion power being able to power us. There is a lot of research going on right now in being able to take a pellet of hydrogen and bombard it with lasers and actually get a sustained fusion reaction from the resulting bombardment. Challenge with the renewables is intermittency. So if you have a gas turbine, that gas turbine can run continuously for 6 months without any servicing. In fact, the record, when I worked for AEP, we had one steam turbine that literally ran for 600 plus days continuous. Recently in California, California has a lot of renewables. There is 100, in Southern California alone, there is 100 megawatts of solar energy that feeds into the grid on a normal sunny day. Recently, it was bright sun outside, and what comes across is a cloud cover. So you watch the clouds roll in, and the power went from 100 megawatts to 10 megawatts in 10 seconds. Now, I don't know if you've talked about things like ramp rates, but you do the math there, and you're looking at a significant negative ramp rate on your power generation. I don't know that you can ramp up a gas turbine that fast. I mean, so how do you compensate for a drop-off in the solar energy when the clouds come by? And this is a real case. Got this directly from the head of the ISO in California, saying this is a challenge that we face. And this is what your generation will have to address. There are some technologies. Gas turbines can come up pretty quick, but I don't think they can do 90 megawatts in 10 seconds. That sounds a little fast right now. What can take that on are batteries. Battery technology is developing right now where I can get things like what are called sodium metal halide batteries. I'll go a little commercial here. You all know what a Prius is, right? So on a Prius, you step on the brakes, what happens? The motors on the wheels turn into generators, and the generators generate power, and there's some storage battery on the Prius that stores the energy. GE's taken this to a whole new level. GE makes locomotives. So imagine turning on the brakes on a locomotive and all the inertia you have driving that locomotive forward. So they're taking that and they're putting this into these sodium metal halide batteries. But these same batteries can be used in the general power grid. Why? The benefit of these? Charge-discharge cycles. They can do tens of thousands of charge-discharge cycles without wearing out the material in the sodium metal halide ion exchange. So significant benefit from that perspective. Again, the issue here is difficult to dispatch. If someone turns on a light bulb in Manhattan and the wind isn't blowing, the windmill cannot be dispatched to provide that light bulb. That's a significant issue with renewable energy sources. This next one here, unfortunately, the slide here didn't. I got to save the font. I didn't save the font. 12 million new DER. DER is an acronym for Distributed Energy Resources. So these are the solars, the biogas, the small wind, and any other type of generation. It's expected that some 12 million devices will be connected to the electric power grid over the next 20 years. Challenge for you, how do you dispatch that energy, control that energy, protect the power system with all those distributed resources around the power grid? So what is protection and control? So I'm sure you've all learned about protection from PROTAP. And protection literally spans the entire grid all the way from the generation side all the way to the power in your home. As a matter of fact, if in my world, you're going to start seeing the utility going into your home. And why is this? Right now we talked about remedial action. Remedial action says I have an emergency situation, I have to shed load immediately. And immediately is in the order of 50 milliseconds. That's how quick these systems have to respond. What happens today is everything gets turned off. An entire feeder gets cut off. Any electricity connected to that feeder is turned off. That's your home. That's the lights on the street corner. That's the schools on that feeder. All get turned off. It's kind of like if having a little sore on your toe and amputating your entire leg. I like to talk about the concept of surgical load shed. Surgical load shed says, let me interrupt only those areas that are non-essential. For example, in your home, if you Pareto the loads in a home, the number one load is going to be your heating, cooling, and ventilating system, HVAC. If you change, I'm going to be precise in how I state this. If you change the temperature at which you're cooling your home, it will instantly turn off the HVAC system, but the user in the home will not see any change for about at least 15 to 20 minutes. So it's something that is benign and doesn't really affect you, the user. Second thing, electric hot water. You turn off the electric hot water heater, no one's going to see for an hour or two that the electric hot water heater is turned off. If you have a swimming pool, turn off the pool pump. If you have a dryer, in fact, you can get a dryer now that will automatically turn off the heat cycle and keep the clothes tumbling. If you have a dishwasher, the dishwasher has a heating element, can be turned off dynamically. What you may not suspect is your refrigerators. Every refrigerator has a defrost cycle. And right now, the defrost cycle is random. I don't need to defrost my refrigerator at 12 noon. By scheduling defrost cycles into the afternoon or evening periods, obviously, you can shift load away from the homes. So in the future, this is where I predict things are going to be going. And I think we're going to be seeing a lot more backup energy. There are now available battery power pods on the order of 1 megawatt that can be located at distribution substations all throughout the electric grid. And we're looking at the concept of microgrids. A microgrid is some generation sources and load that's managed as a small local entity. This happens today in many industrials. Many large industrials will have gas turbines that can provide all their load. They're still connected to the main grid, but if they get disconnected, they are completely capable of operating off-grid all by themselves. So I predict we'll be seeing a lot more microgrids being put into play in the near future. What I don't predict we're not going to see a lot more high voltage power lines built. That's problematic. When I worked for American Electric Power, they built the highest voltage in the United States today, which is 765,000 volts, which is the phase-to-phase voltage on the power line. When I was there, the planning people decided they needed a new line. It took 10 years of going through siting studies, town hall meetings where people would come with pitchforks and spears to the town hall meetings because they didn't want a 765 kV line in their backyard. So it's a kind of trade-off. We want our power, but we don't want to site the power anywhere near our homes or anything else like that. So it's a challenge going forward. This is what I just spoke about. This is the microgrids. This is an actual diagram of a real microgrid that exists up in northern Canada. This is about maybe 300 or 400 miles north of Vancouver on the coast. And they have a hydropower unit, but the hydropower only can provide most of the power during the evening hours. In the daytime, the load often goes beyond the capability of the hydro in the system. So what they have in addition is they have diesel generators. Now at night they have excess hydropower. So what has to happen? And from a management perspective, that excess hydropower needs to be stored and then in the daytime used to power the rest of the little village up there. So we're looking at the concept of microgrid controllers that can optimally dispatch the energy over the course of the operating period of the town. What does this all need? Communications. I'm sure you've all heard the concept of the smart grid. It's not that we had a dumb grid in the past. It's just that now there is a lot more communications. Almost every device that is installed in the grid today has the ability to communicate. And by linking these various communications together, we can start getting better efficiencies as far as how we operate the grid. A system, now in the beginning, so who knows where was the first power line ever built? Anyone? Pearl Street, New York City. This was Thomas Edison. What did Thomas Edison believe in?
DC.
Yes, Thomas Edison was a firm believer in DC. In fact, he was convinced that he could build the DC transformer. He never quite made it, but if he was alive today, he'd be quite pleased because DC is making a comeback in our arena. Why is DC of interest? The ability to direct power flow. DC, by changing the voltage at different angles on the system, can force power from point A to point B. This is not readily implementable on AC power systems. There are some mechanisms that can do this, things like phase shifting transformers and flexible AC flexible AC transmission systems. However, DC does it electronically and can do it much more precisely. So in the future, we're going to be seeing what I call hybrid networks, an AC line that's in parallel with a DC line. Your generation will have to figure out how these all work together and how to control the power flows accordingly. So, what are the challenges to protection and control? The first one is grid stability. What is grid stability? This really goes back to the analogy I gave before of riding the bicycle up the hill. As long as that bicycle can maintain momentum and the bicycle rider has enough horsepower in its legs, it can continue riding the bike uphill. But sometimes the bike hits a pothole. What happens when you hit a pothole? You can very easily fall off a bike. What's a pothole in the power system? A short circuit. Or a line opens up, which changes the path of electricity flow, and it now becomes difficult, if not impossible, to send power from point A to point B. The system becomes unstable, the guy falls off the bicycle, and the power system goes dark. The ability to dynamically detect the incipient instability is very, very critical to maintaining stability going forward. Again, today this is done through, we have some mechanisms in place today. The best one is something called under-frequency. In fact, under-frequency has a direct correlation to our fellow on the bicycle. As the person's going up the hill, what happens? He's going to slower and slower and slower. Same thing on the power system. As you're trying to push more power out, the frequency of the power grid starts going lower and lower. So an incipient detection element is under frequency in the power system. You start to see the power frequency goes down, something is wrong. In Florida has a significant input from the northern areas, from Georgia in particular. Florida will dump as much as 60% of the load in the entire state in order to try and maintain stability in the state of Florida. We've already talked about the distributed resources. And the question is, on the last bullet there, monitoring and replacement of aging protection and control equipment, power system and protection and control equipment. Think of this being in intensive care in a hospital. When you're in intensive care, they'll have all kinds of monitors on you so that if they start to see a failure, they can come in, inject different drugs to maybe get your heart going again, or take specific actions to try and help an ailing patient. Same thing for power system equipment. There are now monitors that can go in. Now, when paper on a transformer starts to fail, the deterioration results in gas. In fact, there are two harmful gases in particular. One is called hydrogen. The other one is called acetylene. These are not very nice gases to have inside of an arena, especially where there might be arcing. In fact, combining arc with acetylene is often disastrous. I have a picture later on. I don't know if it's in this presentation or not, that shows the result of mixing those two together. So, going forward in the future grid, I prefer to call it actually, we're going to be seeing a lot more monitoring. Just like we do with patients today in the hospital, you will outfit your transformers, your circuit breakers, your power lines with monitors, and you will know an up-to-the-minute status of all your assets in the power system. Back to the 2003 blackout. What you're looking at here is a plot of the angle between two lines in the Cleveland, Ohio area. Now, so pray tap, did they know the equation for power? Well, so power is what? V1 times V2 divided by times. All right, this is theta. You did good. So what you're looking at here is the angle across two lines. So that as the angle increases toward 90, you're increasing towards maximum power transfer. Exactly right. What you're looking at here is this one beyond maximum. The angles were getting larger and larger, and see it toward the very end there, how precipitously the angle increases. That is when Cleveland separated from the rest of the world, and then the rest of the world decided, at least the East Coast decided to follow Cleveland into Lake Erie. And it took approximately, I would say, 3 or 4 man-years to create this plot, because they had to create this from historical records, from fault recorders, and the like. Today, this technology is available. These measurements are now available in about 20 milliseconds. This new technology, did you talk about synchrophasors at all? So there is a new technology that's relatively new. It goes back to actually 1979, first identified. It's, let's see, I think I got a picture. Here it is, picture. It's the synchrophaser. So synchrophaser has 2 elements. So first of all, what is a phaser? A phaser is a complex representation of an AC waveform. The first person to identify this was Charles Proteus Steinmetz. He just happened to be a GE employee, but he identified this. He was a professor also. He taught at Union College up in Schenectady. And he identified the use of the synchrophaser, or the phaser, in his 1893 paper. So the phaser is over 100 years old. What was added to this was time synchronization. So at some time t, make a measurement. So as a result, I get an angle that's a function of time and a magnitude that's a function of time. What enabled this to happen is actually GPS, or the Global Positioning System. Now, next question. To whom do we owe the most for GPS? Trick question. Answer, the Russians. For 2 reasons. First of all, what happened in 1957 in the Russians? Right. Sputnik was basically a bomb, but they took out the bomb material and put in a radio. Now, this radio is flying by at some great speed. So what happens to radio wave transmissions when they're moving? And I'm sitting here, and I'm looking at the radio wave transmissions. What do I notice?
Doppler.
Bingo. So there's a Doppler shift. So by looking at the Doppler shift and triangulating, they could figure out exactly where in the sky Sputnik was. Someone then figured out the opposite, said, well, if we know where the satellite is, or a couple of satellites are, I can triangulate down to where I am. And so that was the genesis of the concept of GPS. Now, in the beginning, GPS started out as a Department of Defense program only. And so it was kept inside Department of Defense. And now here's where we thank the Russians again. In 1983, Korean Air Flight 007 strayed into Russian airspace. The Russians shot it down. The then president, Ronald Reagan, said we can't have this happening. So Ronald Reagan, at that time, decided to open up GPS to the world. And so we thank the Russians again for helping open up the market. So that's what enabled this, because the accuracy of GPS, the standard off-the-shelf GPS receiver will hit 100 nanoseconds of absolute time accuracy in a substation. So going forward, everything that we do in our world will be synchronized to the GPS time sources. What makes up a GPS system? Well, we start with the antenna. The antennas are actually active elements. The frequency is coming in, the GPS signal is a once-a-second pulse. And that once-a-second pulse is very, very precise. So the antenna receives this at 1.5 gigahertz, and there's a little amplifier in the base of the antenna, because the signal is pretty weak. It amplifies the signal and then sends it down the cable to a GPS receiver. Now, errors in the system. It takes time for that transmission to go from the antenna into the receiver. What's the time delay? 1 nanosecond per foot. So if I have a 100-foot cable, I have to be able to compensate for about 100 nanoseconds of my time clock. The receiver receives the message and decodes it, and it stabilizes an oscillator. Now, there are many different kinds of, to be precise, there are about 3 different kinds of oscillators that we have in our world today. The most common one is something called a crystal oscillator. Now, there are 3 types of crystal oscillators. There's just the plain crystal oscillator. Then there is a temperature-controlled crystal oscillator, TXCO. And then there is an oven-controlled crystal oscillator, where the temperature of the crystal is maintained at a very constant value. Turns out crystals drift a lot with change in temperature, so you don't want changing temperature because that throws off your accuracy. A crystal oscillator will drift 1 part in 10 to the 9th. So that means for 10 to the 9th oscillations, a crystal oscillator will can have a max error of 1 part out of 10 to the 9th. You can do the math, and let's say I lose my satellite. How much will I drift over what period of time? Turns out you'll drift about 10 microseconds over a 4-hour period. The next type of oscillator is called rubidium. Rubidium has a much better drift stability. It has 1 part in 10 to the 12th. And if you do the math on this one here, this is, I think, about 3 or 4 days before you hit the 10 microsecond level. The last one is cesium. Now, there are some new cesium. Now, to start, the definition of the second is based on the oscillations of the cesium atom. So that's why cesium should be the most accurate, although the cesium's being... So if you do have a cesium clock, that would be the most accurate. What this is here is cesium on a chip, so it's not quite the same quality as having a pure oven-baked cesium clock. But it's close. Anyway, the oscillator comes out and then drives a time sync source. And there are 2 time sync sources we use. Or we had to communicate the time to the devices in the field. And there are 2 mechanisms we use to do this today. The first one is called IRIG-B, and the second one is called IEEE 1588. So IRIG. IRIG is an interesting one. IRIG is an acronym. Stands for Inter-Range Instrumentation Group. This was an Army-based unit that that in the 50s defined a way of encoding time onto magnetic tape for tracking rocket firing. So they would fire a rocket or a missile at time t0, and then time when it lands in the desert some miles away. And so iRig was developed to perform this timing information. There are many flavors of iRig. There's A, B, C, D, E, F, G, and H. Each one has a different characteristic. The utility industry has a de facto standard of level B. Level B says that I send out all my time information once every second. There is an iRig A. iRig A sends out, I send all my time information out 10 times a second. But for us, once a second is quite nice. iRig B runs over a pair of twisted pair wires, whereas 1588 runs over Ethernet, which is interesting. We'll see in a minute. The over Ethernet is known as the Precision Time Protocol. This is relatively new in the utility industry, but you will see quite a lot of it as you go forward. How many of you are familiar with NTP? Anybody ever heard of NTP? All your laptops, when you plug your laptop into a network, guess how you're syncing your time? NTP. NTP stands for Network Time Protocol. So how does this work? I used the example earlier today. If you watch the old World War II movies, the commander is with his troop, and he sits down and says, everybody synchronize your watches. It is now 4:51 exactly. Okay, and everyone goes and pushes the button and synchronizes their watch. What's the error going to be between my watch and everyone else's watch? What are the sources of error? Right. So, if I want to get more precise than me talking, I have to measure how long it takes my voice to go from me, from my mouth, to your ears. Right now, I can say the back row is probably about a 10 millisecond time delay from here to there. So how do I measure that? PTP does that. There are now special Ethernet chips available that are now in the products that protect and control the power system, that when the message is sent out from the device, the Ethernet chip puts a timestamp in a message plus and minus 1 nanosecond of accuracy, resolution. I'm going to use the right word. Resolution is the right word. Not necessarily accuracy, but it resolves the timestamp to the nearest 1 nanosecond. And then I think I got a picture here. Provides messaging, self-organizing. You can have multiple clocks, and the device will choose the best clock. The 1588 compensates for cable length. So if it takes 100 nanoseconds to go from point A to point B, 1588 measures that and can compensate and thus get very, very accurate timing. So in this example here, at time t0, I'll use the mouse. At time t0, there we go. The message is sent from the master clock to the relay. Actually, at time t1, and it arrives at time t2. So the difference between t1 and t2 is the transit time from my mouth to your ear, as an example. Now, you hear the message, and then at time t3, you reply back to me. And I receive it again at t4. So t4 minus t3 is the time from your mouth back to my ear. Now, in this case here, we have symmetry. The time from my mouth to your ear should be the exact same time as from your mouth to my ear. Density of the air staying constant right now. By measuring those 4 times, I can estimate the one-way delivery time from my mouth to your ear. I can calculate this, send that number to you, and you can adjust your clock very, very precisely. In testing done, we were able to achieve 100 nanoseconds accuracy from the clock to the relay. To get to even more detail, the Ethernet, by the way, is ubiquitous now in the utility industry. There is a standard we're going to talk about in a minute called IEC 61850, and it basically defines all communications for power system equipment over Ethernet. Ethernet's a very interesting communication protocol. When you send data from point A to point B, you send it at a certain rate. How does the receiver know what the exact rate of that clock is? We just discussed how clocks can have variance and stability issues over time. Ethernet solves this by telling the receiver precisely what its transmit frequency is. How does it do that? See this square wave on the front end here? It literally sends a square wave. That square wave is precisely the frequency at which it is transmitting. So an Ethernet receiver does something called a phase lock loop. It locks onto the phase of that signal and now knows precisely what the frequency of the Ethernet signal is based upon that phase lock. The Ethernet chip, when it sends the message out, see the red flag here? This is at the juncture of the start of the message. It puts the timestamp right there at that point. And it timestamps that again to the nearest 1 nanosecond resolution. This is an example of how it's calculated. I'm not going to go into that now. But now let's go into the rest of the synchrophasors. Has anyone here ever had a motors lab? Is there a motors lab here? No? Yes?
I did.
You did? Many years ago. I had a motors lab a long time ago also. And one of my favorite experiments in the motors lab, we had a synchronous motor. And you had a strobe light. And the strobe light was set to power system frequency. So it flashed at precisely 3,600 flashes per minute. When you took the strobe light and put it onto the shaft of a machine, of a synchronous machine, it would look as if the shaft was standing still. This is exactly what a synchrophaser is. A synchrophaser strobes the power system. In fact, the analogy I like to use, if you've ever been to a dance with the strobe light. So when you're in the dance, you go to the dance with the strobe light and you look at people, people have this kind of jerky motion because the light only shines at particular instants of time. This is what a synchrophaser does. A synchrophaser strobes the instantaneous phase angle and magnitude at different points in time of the power system. The power system is never, or almost never, standing still. In fact, you know, one of the great models of a power system is a bunch of springs, masses, and dashpots, all connected together with all kinds of pins. And as you change the configuration of the springs and masses, everything oscillates for a while until it reaches some kind of a steady state. So the power system is always moving. Synchrophasers let me see that oscillation. So if again, the analogy here is with the generator. If took a if a machine is operating at exactly 60 hertz, and my strobe light is flashing at exactly 60 hertz, it would look as if the rotor of my generator was standing still and not moving at all. Observation. If the generator is moving slightly greater than 60 hertz, the synchrophaser is going to rotate counterclockwise. If the frequency is slightly less than 60 hertz, it's going to move clockwise. This will be in the test, I think. So in general, the definition of a synchronized phasor measurement is the phase angle and magnitude of an AC waveform at a particular instant in time. The synchrophasor is referenced to a universal cosine wave. So imagine a cosine wave that goes from minus infinity to plus infinity, and that at any instant in time, the peak of the cosine wave is at fraction of second 0. Okay, now what's fraction of second? So if I count seconds, I have second number 1, second number 2, second number 3. Between second number 1 and second number 2, I have fractions of a second. So we talk about top of second number 1, top of second number 2. Top of second means the fraction is 0. So the cosine wave is at 0 degrees at top of second. And then along comes my GPS pulse that says, make a measurement now. So here is my GPS pulse coming in on my AC waveform. I measure the angle from the top of the cosine wave to where the timestamp comes in. That has an angle theta. That is the absolute angle of a synchronized measurement. That measurement point also has a peak of the fundamental waveform. The synchrophaser only looks at the fundamental frequency. It does not look at any harmonics in the waveform. In fact, the standard says that you shall reject any harmonic measurements from any synchrophaser measurement. So the synchrophaser has the magnitude, the angle, and the timestamp. So if I take the entire power system and I strobe the entire power system with my GPS clock, I get a measurement at every node in my power system that is made at the exact same instant in time. That gives me the instantaneous state of the power system. The first implementation of the synchrophaser was done using something called the Fourier transform. The Fourier transform correlates a fundamental frequency with whatever waveform you are measuring. In the case of a 60 hertz waveform, I'm looking at the correlation of a sine and a cosine wave with the 60 hertz waveform. And I get a phasor, as shown here. Assuming that I'm off nominal frequency, that phasor is going to rotate around, as I kind of discussed. It turns out that if you plot the phasor, it does not describe a circle. This is you can prove this on your own at home. It describes an ellipse. And the standard says, oh, this is nice, but we don't like ellipses in the power system. We want a circle. So the standard says, figure out how to turn it into a circle. And so all the vendors who implement these synchrophaser measurements are responsible for do the mathematics to convert it into a circle. Break time. I just want to check. Is there a break time scheduled? No break.
You want break?
I'm good. Are they good? They seem mostly awake right now. It's good. Actually, it reminds me back in college, we had this particularly boring chemistry professor, and this guy fell asleep in the front row. So the professor goes to the girl next to him, "Get him up. He's not going to sleep in my class." The girl paused a moment and said, "No, you put him to sleep, you get him up." I don't know what she got in that class. All right, so going forward, we're looking at synchrophaser systems. The system has a GPS clock that is synchronizing the measurement made on the voltages and the currents in the power system. And I get many, many measurements from the entire power system. I can now see the dynamic state of the power system. In fact, future here, in fact, I don't know if do I have this in here? The future is going to be using these measurements to dynamically predict instability. Two things. So number one, to predict instability. And then number two, this is where the challenge comes in, how do I automatically correct for the instability? How do I figure out what loads I'm going to throw out of my backpack to keep my bicycle rider from falling over? Because when he falls over, the lights go out. Today, utilities are building synchrophaser systems in a hierarchy. The hierarchy says I have a measurement in a substation. The substation, the data gets collected by a device known as a phaser data concentrator, often abbreviated as a PDC. The phaser data concentrator sends it up to the local controller. The local controller then sends it up to the what's called the independent system operator, and then the independent system operator may choose to send it to Department of Homeland Security, wants to know what you're all doing. I think they're in cahoots with NSA, but as we look to the future, however, there are going to be new applications of these measurements. For example, if I look at over a wide area and I start to see the angle between two areas, like I saw up in Cleveland before, getting way, way too large, I can declare a dynamic out-of-step condition and actually trip off and break the system in half to prevent both systems from knocking one another apart, which means I'll be communicating between, PMU, by the way, is phaser measurement unit. I'll have a need to communicate between phaser measurement units. So we're going to test now. How many people here, so you know what protection is, right? What is backup protection? Exactly right. Synchrophasors provide an interesting backup protection mechanism. Synchrophasors give me very, very precise currents at two ends of a power line. And what does Mr. Kirchhoff tell us about currents through a power line? Exactly right. So if in real time I take the synchrophaser measurements at both ends of a line, add them together, they better be equal to almost zero. Why is it not going to be exactly zero? You talk about line charging? Line charging current. So if I have a long line, there's a bunch of the current that goes into ground. So the difference between the two ends will be equal to the amount of current that's sucked up by the capacitance of the overall power line. See if I'm tying everything together here. So anyway, what that means is I'll need to be able to talk between phaser data concentrators. And talking in that way there, I'll be able to compute and provide backup protection for power lines. Today's protection engineer has to have a certain amount of communications background also. So if I'm sending measurements, I'm communicating from a substation. Right now, the protection engineer has to tell the communication engineer how many bits per second the communication line from that substation to a remote location must be able to handle. In this case here, the frame rate dictates the bandwidth required. So if I'm sending measurements from my substation at 30 frames per second, and I'm sending VA, VB, VC, you see the list there, IA, IBIC, V1, V2 frequency, etc. I need 160,000 bits per second of bandwidth on my communication channel. On the high end, if I go to 120 frames per second, I now need 640,000 bits per second communication from my substation to my remote locations. So that's why today's power system engineer also has to be a communications engineer. So this is interesting here. So let's say I'm storing the data now. As the data comes out, I'm going to store it for analysis. Sending 6 PMUs, the data from 6 measurements, 6 lines of data, is 92 bytes per PMU. And then for 6 PMUs, that's 552 bytes. So that's 66,000 bytes a second, 4 megabytes per minute, 238 million bytes per hour, megabytes, 5 gigabytes per day, 171 gigabytes per month. Lots of data storage. In fact, if anything, and it's 2 terabytes per year. So the engineer has to say, why do I have to save everything? And you don't have to. What do you really want to know? You want to know when something happens. So inside the message, there are trigger bits. The PMU says, hey, I see an overfrequency. Hey, I see a line out. Hey, I see an overcurrent. So by carefully analyzing the trigger bits in the message, I can be judicious as to how much data I choose to save in my storage system. This one here is interesting. Where are we going worldwide with communications? Cisco estimates that by 2016, the yearly data traffic on the internet will hit 2 zettabytes. So this is a new one for you. A zettabyte is 2 times 10 to the 20. So a zettabyte is 1 times 10 to the 21st bytes per year. This is what we're heading towards on a clear path right now. And by the way, all of your next Netflix streaming is accounting for about 40% of that, if not higher than that. The technology needed to keep up with this, they're already looking at 100 gigabit Ethernet. 1 gigabit is very common today. Many devices have 10 gigabits. And again, the technology is heading toward 100 gigabits over a fiber optic link. All right, next section, communications. As you've seen, the ability to put intelligence into what we're doing is truly a function. You can throw it up. He came prepared. So communications is key as we go forward. There is a new worldwide standard, new meaning the work on this started in 1995, and the first draft of the document came out in 2003. We have recently released edition 2, and we're now working on edition 3. I say we because I'm part of the working group that's been developing this since 1995. One of the technologies that we're using in communications is called object-oriented methodology, OOM. Am I familiar with C++ and the like? Okay, so this is all object-oriented communications. In the beginning, we had protocols like Modbus and like, do I have a picture of it here? No. We had protocols like Modbus and DNP. What these protocols were effectively big Excel spreadsheets. And you had data in cell A1, A2, A3, A4. What does it mean? When the data came across, it literally came across. Here's the contents of A1, here's the contents of A2, here's the contents of A3. There was no semantics or meaning to any of the data being communicated. This is now changed as we migrate to this new communication protocol called IEC 61850. And the concept is pretty straightforward. We start with the idea of an object. So in a substation, I have a real physical circuit breaker. A circuit breaker has characteristics. So let's do a little object modeling exercise here. What's the first characteristic you would think of a circuit breaker? Again? Current ready? Current rating. Okay, well that's a name. That's a part of it. That's the nameplate of the circuit breaker, and that is part of the model. What else? Contact status. Are the contacts open? Are the contacts closed? How fast are the contacts open? How fast are the contacts closed? When's the last time the contacts opened? When's the last time the contacts closed? These are so we just did a little bit of a modeling exercise here, and this is exactly what groups like this did for the past 15 years. Is they would sit down and say, okay, I want to model gas and oil. So what are the different gases I can possibly find in oil? And they made a list of all the gases that are presently analyzed, and this list took on standard, internationally standardized names for all the gases. So CO2 is pretty obvious, H2 for hydrogen, O2 for oxygen, and things like that. So models were made of all these different physical and logical devices. What's a logical device? A relay. Although there's a physical device, check synchronization is a good angle. You know, who knows what check sync is? They should know this one, right?
We didn't cover much on that.
Didn't cover. So anyone know what check sync is? Let's see. What's a good example? If you have two gears kind of getting ready to mesh on a car, if the two gears aren't aligned when you release the clutch, what happens? You get well, it's auto reclosing, but it's a specific kind of auto reclosing. Remember, if the angle between the two ends of the line is very large, when you close the line, what's going to happen? And get a lot of power flow through that line instantly. Not good to do. It really puts a lot of stress on the contacts of the circuit breaker. So what often happens is I have a phaser at one end of the line and a phaser at the other end of the line. And if the systems are isolated, which happens sometimes, the phasers will be rotating. In fact, case in point is, let's say you have a factory, that the factory has generators, and then the power system has generators. The two of them will not be synchronized. What will happen? The two phasers will be rotating at some angle. If I close when the angles are 180 degrees apart, what do I get? Short circuit. I get a short circuit because the voltages are literally opposite one another. So where do I want to close? That's 0. So I want to look at the angles in real time, and I want to make sure when the angles are aligned, then I issue the reclose function. This is all modeled in 61A50. So 61A50 says, what is the phasor magnitude and voltage for the bus voltage? What's the magnitude and angle for the line? If the angle is less than a certain setting, enable the line to reclose. And this is all part of the modeling exercise. So if I have, what we start with is a model of a real physical device. Given the model, what do I want to do with this? Communicate the data. To communicate, we use what are called services. I'm an old Fortran programmer. I'll show my age here. And we got two of us. Use Fortran also? Right. Fortran had subroutine calls. If I wanted to create a file in subroutine, there was an open function. Say open, and you put a bunch of parameters in, and that would go and open a file on the server in the computer on which you were working. If you wanted to put data into the file, you would use a function called write. You'd say write, and then give it an address of the data you wanted to write. So open, write, close are services that are provided by the Fortran language. In 61A50, we have services also. What do I want to do with the data? I want to get the data. It's as simple as that. But in English, we actually use the word get data is the actual name of the service in 61A50. If I want to put settings into a device, I want to put data. Let's say I've captured a file for oscillography. I want to get file. If I want to put settings in for the whole relay, I can put file, which is the settings for the entire relay. So 61A50 consists of data models and services to access and to work with those data models. So this is the new world of communications for the utility industry. Specifically, there's one feature I want to focus on that 61A50 brings to the party. So if I didn't know this person here, I could walk up to him and say, who are you? He could say, my name is Pratap. I used to work for Excel. I now work for HDR. I'm teaching a class on power systems. He could completely describe himself to me. 61A50 has this as a built-in function. So as a client, when I first connect to a relay or any IED, by the way, IED is not improvised explosive device, is intelligent electronic device. We've been having a debate in the industry how to change the name. So far, we haven't gone past IED yet. But when I first communicate to the IED, I can say to it, who are you? In response to that request, the IED will tell me all of the models it knows and all of the services it supports. So it can completely describe itself to me. And this is significant. We talked about 12 million distributed energy devices being established on the power grid. Just think of how many engineers it would take to go and to talk and to configure every one of those if it had to be done all manually. This is the self-description piece. A special feature was identified in 61A50, and this is, now, normally, when you're on the computer, when you're on a web page, you're using a communication model known as client-server. You're the client, and you ask for information from a web server somewhere on the network. That model works good on a one-to-one basis. However, in the power system, and this one here didn't print out too well. The names got lost on there, but there is an application where I want to where I, as one relay, want to send information to many, many other relays. This is known as the publish-subscriber model. Think of the New York Times. The New York Times publishes a newspaper. If you are interested in what the New York Times has to say, you subscribe to the New York Times. So this is the publisher-subscriber relationship, a one-to-many relationship. Now, presents some challenges because how do you know if the publisher's alive or if the subscriber is alive? So, as an example, let's say you get a paperboy. In fact, paperboys barely exist anymore. I used to be one years ago. If I forgot to deliver someone's paper, I wouldn't be home 10 minutes before I get a phone call saying, "Where's my paper?" All right? This exact same concept is built into this publisher-subscriber model. So when I publish a message, in the message I state, I will deliver the paper same time tomorrow. If I don't deliver the paper same time tomorrow, guess what you're going to do? You're going to call me and say, "Where's my paper?" This is exactly the messaging system that's been defined here. 3 primary requirements. Number 1 is reliable message delivery from one to many, publish to many subscribers. Number 2, it has to be fast. We're looking to get a message from, this is machine-to-machine communication. We talked about machine-to-machine communications. This is one of the fastest machine-to-machine communication mechanisms around. Less than, the standard requests 3 milliseconds. We actually do it right now in 1 millisecond on the average, 2 milliseconds max. And it has to, again, be reliable. The name for this is the Generic Object-Oriented Substation Event, or the GOOS. And the GOOS is a publisher-subscriber message. It's a multicast. Multicast is a special feature of Ethernet. It turns out if bit 8, so an Ethernet address has 48 bits in the address space. If bit 8 of that address is set to a 1, it identifies that message as a multicast message. So what I'm doing right now is called broadcast. I'm sending a message to everybody in this room. Multicast says this message is only for people in the 3rd row back. Using devices such as Ethernet switches, I can filter the message so that the Ethernet switch only delivers it to the people in the 3rd row. The rest of you never even see the message. This is a concept of multicast. It's supported by Ethernet. The GOOS is primarily designed for local area networks, but today's communication technologies let me expand that well beyond using something called virtual local area networks. In fact, if you think about what is a local area network, in the beginning, Ethernet was defined on a piece of copper wire. That was a local area network. As I took 2 local area networks, I connected them together with a router. But today, I can create virtual local area networks, where I have a piece of copper here that is virtually connected to a piece of copper in New York City. And that's called a virtual LAN, or VLAN. And I can send a message on this one network here, and it literally finds its way to New York and to the local area network in New York City. The data on a local area network is not routable. Routers connect multiple local area networks together. So a goose message will not normally go off of a local area network. The goose is sent on change of state. So when something happens in the relay, for example, a breaker opens, the goose is immediately launched. But 99% of the time, nothing is changing state inside of the substation. So how do you know that I'm still alive? So I periodically resend the same data. And again, if you don't hear from me in a specified period of time, you can say Mark's goose is cooked, and you need to go and find out what the problem is. We get reliability by message repeat. Now, you've probably all heard of TCP. In fact, you always hear of TCP/IP. TCP is the Transmission Control Protocol, TCP. What does it do? When I send a message, say, hey, Dave, where are you? He comes back and says, what? I didn't hear you. I repeat again, say, Dave, where are you? So it allows for retransmission of messages. You see how long that took, though, to go back and forth with TCP. So TCP does not work for fast messaging. So what do? I say, Dave, where are you? Dave, where are you? I repeat the message many, many times. And he's either deaf or dumb or very slow responding then. If he doesn't get the message, that is. So this is how Goose works. This is very, very fast. There is a new Goose out now. I don't know if I talk about it here. I do. So when Goose hits the router, it dies. It goes into the bit bucket. There is a new mechanism now called the routed Goose. The routed Goose adds an IP address layer to the Goose message. So now the Goose can now transit through a wide area network using multicast addresses. Now you all know multicast. How many of you ever listened to internet radio? Anyone? Yeah. When you're listening to internet radio, you're listening to a multicast broadcast. So I have the one publisher is sending out a message, but it's going to many, many devices all over the world. And literally it can go over the world. And that's multicast, but it requires a special IP address. There's a special range of addresses that are allocated for multicast. Wherever you want to use these, Synchrophasors. So let's say Xcel Energy computes a measurement at one of its substations. They might want to share that information with their neighbors all around them. They would use a routable multicast synchrophasor message to send those values to all of their neighboring utilities. And we'll skip this one here. Now, I had a proposed name for this. So what would we call a networked version of the Goose? The networked object-oriented substation event or the noose? People got hung up on the idea. In fact, the working group turned me down flat. But I did propose it, though. And so there is something called a routable Goose and routable sample values. I really didn't talk about sample values, but sample values is how we send synchrophasor information on a periodic basis to many, many different locales. And basically, it adds an IP address to the message, which gives it the routability over the wide area network. There's an interesting feature in the Internet Protocol called differentiated services. If you've ever been to Disney World, and you get on a line, and sometimes the line can be very, very long. And you're standing in line, and this person comes up behind you and goes right to the front of the line. Why? They paid for differentiated services. They said, we paid for priority, we want to go first. It turns out this is part of the new synchrophaser routing mechanism. Synchrophaser packets can get priority routing. So when they come in, they go right out. No delay in the router. And this is just a comparison between, let's say, between multicast and unicast. In unicast, I have this red dot here, and this red dot is sending out, where's my mouse? The red dot is sending out 3 different streams to the 3 different red dots. 3 green dots, sorry. In multicast, the red dot sends out 1 stream. The router splits the stream into the different paths as needed. But how does the message know how to find you? When the message gets sent out from the publisher on this left-hand side here, it hits the first router, and the first router says, I don't know what to do with this. This is a multicast message. It can go anywhere in the world. So there is a new, again, I'm turning you into communication engineers here, but there's a new communication service called the Internet Gateway Management Protocol, IGMP. IGMP, you're over here as a Synchrophaser subscriber that says, hey, I want to listen to Mark's Synchrophasors. So you send out a request here that says, go find a path to Mark. And the message goes out to all the routers in the network looking for Mark. When it finds Mark, it leaves breadcrumbs behind in all the other routers. So now, the main router here can now find a path to get the message to Mark as the subscriber for the Synchrophaser. Obviously, I can have many, many subscribers. Each subscriber creates its own path. Security, we seem to have a national paranoia about security now. NSA has helped us a lot, and also all the attacks we get from other countries around the world. Although most utilities have internal networks that are non-routable, but still we put in cybersecurity features anyway. There are 3 primary aspects of putting together a cybersecurity system for these publish, subscribe messages. The first one is called authentication. How do I know that this message came from Mark? And there's a concept known as authentication, which I sign the document with something called a certificate. And the certificate is something that, and when I sign it with a key that I have. And that the key is exchanged between me and the subscriber. The only way that the 2 people could have communicated was if they had the same key and run the same communication network per the certificates. So this is a way of what's called non-repudiation. No one can repudiate that this message came from Mark because Mark's the only one that could have signed it with his signature. Second aspect you all heard of is called encryption. I can take the message and I can encrypt it using a key so that it is unintelligible to anyone that intercepts the message. Then the third aspect of this is called the key exchange. How do I exchange keys from me to many, many subscribers? And there is an again, the internet has been very, very active in this area. There's a standard called the Group Domain of Interpretation, which is a protocol for exchanging keys in a multicast scenario. Let's skip this stuff here. Some application examples, and this is some stuff that Pratap has been involved in recently. As the power system becomes more diverse and we mix electronic loads in generation with electromechanical loads and generations, we get strange interactions. One of them is oscillations. What you're looking at here is a real oscillation on the Southern California Edison power system on September 13th, 2000. What you're looking at is the 230 kV voltage here in normal pre-fault state, and then these little wiggles here represent a fault, trip, high-speed reclose. Fault, trip, high-speed reclose, and then finally fault, trip, lockout. In the lockout mode, the power system developed a sustained oscillation. Imagine two generators swinging back and forth against one another at very, very slow speeds. The frequency of that oscillation there is 0.6 hertz. Very, very slow. I was talking to Pratap earlier. He said he's seen some of these oscillations now as high as 13 hertz. This is extremely destructive for the power system. It's kind of like you're on your bicycle and you're pushing forward, pushing back, pushing forward, pushing back. Think of the stress that puts on the chain on your bicycle. This puts stress on the shafts of the generators. Synchrophasors allow us to detect that. The schemes to detect and to remediate these, again, are called remedial action schemes. This is one being developed right now by Southern California Edison. This will span the entire southern portion of California. The scheme is pretty straightforward. On the left-hand side are monitoring devices that monitor the status of power lines, open and closed, and whether or not they are overloaded. This information goes to a logic processor. The logic processor then does basic logic that says, if this line's overloaded, and this line is overloaded, and this line trips out, take action. The action right now is shedding load, and these are the mitigation devices that are connected to the distribution feeders that go and shed load. Let's go some of these. We can make all kinds of pretty pictures with this information by plotting the phasors out. This one here is an interesting one. Imagine I have a puddle of water, and I drop a stone in the puddle. What do I get? I get a big hole where the stone goes in, and then I get a wave going out from the middle of that puddle. How fast will that wave move? It's a function of the viscosity of the liquid in which I drop the pebble. Well, it turns out the power system is very viscous also. When you drop a power plant in the power grid, what happens to the frequency there? At that very center point, it's going to go to zero, of course, because the generator is going to trip offline. But it sends out a ripple of frequency. And what you're looking at here on these diagrams is that ripple spreading out from the center of where the power plant went out. And this frequency is a wave. In the East Coast, it travels at 350 miles per second. On the West Coast, it travels 1,100 miles per second. Why? Much, much longer lines with fewer interconnections and the like. Let's skip some of these here. I'm going to go to some of my favorite ones at the end here. This we talked about already, the zone of protection. Synchrophasors can be used for dynamic line impedance calculations. By measuring synchrophasors at both ends of the line, I can do a very, very simple Kirchhoff's voltage rule. Sum of the voltages equals 0. So V1 plus the voltage across the line plus V2 equals to 0. So by taking synchrophasor measurements at the two ends of the line, I can compute the voltage equation and literally compute the dynamic line impedance.
It's 545, right?
It is 44.
Still. No, just I wanted to just.
Yeah, we'll finish up here with I think I have one. We talked about microgrids already.
Battery system.
Yeah, so things for the future, battery systems. These will help level off the intermittencies of renewables such as solar, such as wind. This one here happens to be a 1.2 megawatt system. There are now, the AEP has a 7 megawatt battery on their system now.
Who makes the batteries?
Well, it's an interesting question.
Batteries.
They used to. They used to make what's called the sodium-sulfur batteries. Sodium-sulfur wasn't too stable. The factory burned down. So GE is now making one. GE is making actually the sodium metal halide. And that's made in Schenectady, New York right now.
We have one installation here in southern Minnesota, in Laverne, Wisconsin, in Minnesota, south of Minnesota.
So I'm going to jump into, I have one neat last slide here we'll finish up with. Well, there's a lot of stuff here yet. Technology advancements. Okay, so aging infrastructure, monitoring devices is clear. Fiber Bragg sensors. This is a neat technology. Fiber Bragg sensor takes a piece of fiber optic cable and replaces sections of the core of the fiber with sensing elements. The sensing elements could be temperature sensing, pressure sensing, gas sensing. So as their temperature changes, the refractive index of the core of the fiber changes, and I get a refraction back that is directly proportional to temperature or gas or pressure. Expect to see this used a lot more in the very near future. Optical quantity measurements. There are now optical voltage transformers, optical current transformers that use the properties of optics to measure current and the properties of optics to measure voltage. Michael Faraday, over 110 years ago, identified that when you took polarized light parallel to a magnetic field, the angle of polarization would rotate in direct proportion to the magnetic field. So that's how the current sensors work. That's the same thing here. Copper will be replaced by fiber optic as we go forward. It's very expensive. People like stealing copper out of these holes here. Every so often you find a dead stealer that pulled the wrong wire out, especially CT wires. And we'll finish up with one last. I had a lot of slides here.
This is the full course.
Yeah. Nanotechnologies. Fiber nanocarbon tubes are going to be used that be ultralight and ultra strong, and we'll see them throughout many, many building devices, especially things like windmill blades will be lighter and stronger. Nanocoating, so this one we're going to finish off with. So what we have here, I hope this works. This might not work. And the reason is I didn't copy it over. What this is going to show you is, ever heard of hydrophobicity? Super hydrophobic materials. So hydrophobic means it's afraid of water. Okay? What we have here are two glass slides. One is a pure glass slide. The other one is coated with a super hydrophobic material. And if you want, I can finish up with one last picture, but I need to, I guess I can just copy it over into here.
It's a very nice slide where it's nice to see this.
You can connect this video to.
I gotta get it off here. Didn't get cut.
When Mark showed that oscillations, interarea, that is the inter-area oscillations. If you have two systems, group of generators working between two stations, they always oscillate at less than 1 hertz. That is called quarter hertz oscillations. And then when Professor Wallenberg teaches you stability, you see that that gets amplified and the whole system falls apart. Or within one system, also between generators, they are not running at 60 hertz. Sometimes there can be 1, 2 hertz or 3 hertz difference between the two. And if you have a series compensated line, the capacitor oscillates with generators and then produces subsynchronous oscillations, which is around 9 to 13 hertz. So depending on that, you get varieties of oscillations, and they can look at it and then create and determine. And if you look at the inter-area oscillations, if you look at the damping of the signal of the quarter hertz, then you can decide whether the system is going down or not. And they can easily separate the system and take care of the system. Every time, whenever there is a blackout, they go back and study that, and then they found that the damping ratio went below 1 or some 0.5, and then they do that. But right now, we have devices which tells you that you are already at the edge of the system and you might fall apart within no time. That is available now, which was not before.
Okay, I'm just copying them.
You can connect it here itself.
Oh, can I?
Except that it is, everything else is here.
Maybe.
Done that.
All right, so here's the honey one here. So we're going to see 2 drops of honey, one on a pure glass, on a glass slide, one coated with a super hydrophobic coating. So that's the glass slide. Honey just sits there. Here is the coated slide. That's sticky honey. That's the first one. Now, water normally has a cohesion, surface tension. So when you put water on, it usually sticks to the surface. In fact, if you have curved surfaces, water will roll around the curved surface, except if it's coated with a super hydrophobic coating. So here is a drop of water hitting a super hydrophobic coating. All the droplets recoagulate, and the water bounces off the surface of the material. Now, this drop of water is actually floating up. This is very, very slow photography. So it's floating up. Now, look at those little droplets there. They're kind of just literally floating on top of that super hydrophobic coating. And if we wait patiently here, watching paint dry and water fall, the drops coming down right now should be coming into view momentarily. Again, it's very slow photography. Very slow photography. Here it comes. Hits, bounces, and away it goes. All right, so I'll conclude with this. The future is bright. There are a lot of technologies that need to be applied, and it's up to you to do it. All right, thank you very much. Okay.
Mark and I thank you.
Pleasure.
If you have any questions, please do send me an email or so, then I can send it to him. So when he's sitting in a plane, hello? Know that. Thank you very much.
All right.